Self-organization in AI to 1. Introduction. Self-organization refers to the ability of a system to spontaneously develop structured patterns, order, or functionality without explicit external control. In the context of artificial intelligence, AI, it describes how intelligent behavior, representations, or network structures can emerge from decentralized interactions among components, often driven by local rules, adaptation mechanisms, and feedback loops. Self-organization in AI borrows heavily from ideas in complex systems, neural networks, and emergent computation, aiming to replicate the way natural systems, biological brains, ant colonies, ecosystems achieve high-level organization without centralized design. Second core principles: local interactions, global patterns. Components, neurons, agents, modules follow simple local rules. The interplay between these rules creates coherent large-scale behavior. Feedback loops. Positive feedback amplifies promising patterns. Negative feedback stabilizes or prunes unproductive structures. Adaptation and learning. Systems adjust to environmental inputs and historical performance. Learning can be supervised, unsupervised, or reinforcement-driven. Emergence. New capabilities or representations arise that were not explicitly programmed. Examples: spontaneous feature hierarchies in deep learning, cooperative strategies in multi-agent systems. 3. Historical context. Era. Key developments. Impact on self-organization in AI. 1940s to 1950s, cybernetics and early neural models, McCulloch-Pitts neurons, introduced feedback control and distributed computation concepts. 1980s, self-organizing maps, Cohonen, Hopfield networks showed how unsupervised learning can produce topological organization. 1990s to 2000s, genetic algorithms, swarm intelligence, applied self-organization to optimization and robotics. 2010s to present, deep learning, reinforcement learning, self-play, demonstrated large-scale emergent behaviors in complex environments. Fourth, mechanisms of self-organization in AI. 4.1 Neural plasticity and Hebbian learning. Mechanism. Connections strengthen when units activate together, fire together, wire together. Effect. Clusters of neurons develop specialized responses without explicit labeling. Example: early layers in convolutional neural networks, CNNs, learn edge detectors spontaneously. 4.2 Competitive learning. Mechanism. Units compete to represent input patterns. Winners update weights. Effect. Feature maps that partition input space efficiently. Example: Cohonen. Self-organizing maps arrange neurons to reflect data topology. 4.3 Evolutionary algorithms. Mechanism. Populations of candidate solutions evolve via selection, crossover, mutation. Effect. Problem-solving strategies emerge over generations without explicit programming. Example: evolved robot morphologies adapting to terrain. 4.4 Swarm intelligence. Mechanism. Agents interact via local rules, e.g., pheromone trails in ant colony optimization. Effect. Efficient global search, resource allocation, or pathfinding. Example: distributed drone coordination for search and rescue. 4.5 Reinforcement learning and self-play. Mechanism. Agents explore actions, receive rewards, and adjust policies. Effect. Emergence of novel tactics beyond human input. Example: AlphaGo discovering unconventional Go strategies. 5. Self-organization in modern AI architectures. 5.1 Unsupervised representation learning. Deep autoencoders, variational autoencoders, VAEs, and contrastive learning methods discover compact latent structures without labeled data. Emergent features can transfer to downstream tasks, demonstrating adaptability. 5.2 transformers and attention mechanisms. Even without explicit structure, attention heads self-organize to track syntactic or semantic relationships in text. Some heads develop roles like subject-verb agreement tracking without being told to. 5.3 multi-agent systems. Agents develop cooperative or competitive behaviors through local interaction rules, useful in robotics, simulated economies, or virtual environments. 6. Benefits of self-organization in AI. A scalability. Systems adapt to complexity without micromanagement. B. Robustness. No single point of failure. Distributed structure is fault-tolerant. C. Adaptability. Rapid adjustment to new environments or tasks. D. Innovation potential. Novel solutions can emerge beyond human intuition. 7th, challenges and risks. A. Unpredictability. Emergent behaviors can be beneficial or harmful. Interpretability is difficult. B. Control and alignment. Ensuring self-organized AI aligns with human goals is non-trivial. C. Evaluation metrics. Hard to quantify good, emergent structures without clear objectives. D. Resource consumption. Large-scale self-organization can require significant compute and data. 8. Case studies. 8.1 DeepMind's AlphaZero. Used self-play to master chess, Go, shogi from scratch. Self-organization emerged in its search heuristics and piece coordination patterns. 8.2 Neural cellular automata. Networks learn local update rules to grow complex structures, used in generative art, damage repair simulations, and artificial life research. 8.3 Self-organizing traffic control. Distributed controllers at intersections coordinate based on local sensor data. Results in adaptive traffic flow without centralized scheduling. 9. Applications. Domain. Example. Use case. Self-organization role. Robotics. Swarm exploration. Agents coordinate via local communication to cover terrain. EACT. Natural language processing. Transformer attention. Heads specialize in linguistic tasks without explicit labeling. Cybersecurity. Intrusion detection. Networks. Adaptively cluster traffic patterns to flag anomalies. Healthcare. Medical image segmentation. Unsupervised feature maps detect relevant anatomical structures. Finance. Market simulation. Agents evolve trading strategies through repeated interaction. 10. Future directions. A hybrid self-organization plus human guidance. Combine emergent adaptation with human oversight for safe exploration. B. Explainable emergence. Tools to visualize and interpret how organization arises. C. Adaptive modular AI. Systems that reorganize modules dynamically based on task demands. D. Cross-disciplinary inspiration. Drawing from biology, sociology, and physics for richer local rule sets. 11th conclusion. Self-organization in AI is a bridge between mechanistic computation and emergent intelligence. By enabling systems to create structure and capability without micromanaged instruction, it opens doors to scalable, adaptable, and innovative solutions. However, its unpredictability and potential misalignment mean that developing interpretability, control mechanisms, and ethical oversight will be essential for safely integrating self-organizing principles into the next generation of AI. Read my previous blogs at https://www.patreon.com. Steve Hovland. If you get value from these blogs, please consider joining my Patreon as a member at the $1, $2, or $4 level.